Maybe it's better to close. Okay, shall we start? So we had a lot of information today, and still I think we need to digest these information, and also some information is preliminary. So one thing we have to do here is to again list up what we really need for by the tomorrow, and also as a first discussion, I think it's better to check clarify for each technology which is a major concern and how we feel that point. So, okay, as I said in this morning, I made the Excel file, but I don't. It's useless to discuss one by one. But I think it was just to discuss for each technology which is a major concern at the moment, and then what should be our recommendation. So shall we start from the planar sensor? So what is the major concern or issue for this? Nothing?
I think it has to be...
Microphone, please.
Oh, sorry.
I mean, for the planar, I think it has to be the secure. I would say it was the security of the high voltage operation, which to some extent, I think, perhaps one of the presentations we were about to have might be relevant, which is the how you actually make the stave and make it high voltage secure. I think because the power is still dominated by the front end chip, then the difference in power between the two options is a lesser concern. So I think it's the 1,000 volts which takes us into, if you like, unfamiliar territory.
Okay, so you think that power itself is still safe?
On the cooling presentation that we are hopefully going to get somewhere.
Tomorrow morning, I think we will get.
For the cooling, I mean, you haven't seen the presentation yet, but I tried to wrap it up. Okay, we had 10 engineers working for the last 2 years to design the stave primarily for the cooling. We've made a number of critical decisions along the way in order to have the maximum cooling headroom. This was, first of all, go to CO2. If you remember, we had C3F8 in mind some while ago, in order to run at -40 then instead of -30. Second, we went to titanium pipes instead of carbon fiber to have a minimal temperature drop along the pipe wall for the very same reason. It gained us about 5 degrees. And we went to carbon foam as you had to have a good thermal conductivity on the stave. Net result of all that was a stave with a thermal figure of merit of about 12. Now what does this mean exactly? This means, and Eric will show this tomorrow, we've built a number of prototype staves, and the one for the final layout was tested in a range up to, I need to look it up in the plot, I think 3 watts per square centimeter. Now our max for IBL is 0.5. 300 milliwatts on the chip and another 200 milliwatts on planar sensors. This brings the stave sensor temperature on the stave as measured on silicon heaters in this case, in the range of -30 degrees to -25 degrees. So this is 0.5 up to 0.8 watts per square centimeter. So in this power range, this sensor temperature is measured on dummy staves installed very much in the area. So from that measurements plus the simulations that go with it, I would judge we have about 10 degrees headroom from the stave we know now to is minus 15 degrees. So I would say for the cooling, this is, and that's why I made the statement before, the cooling specs stand with minus 15, and personally I'm not worried that we have a problem with Plana on that. And the concern on the high voltage is an obvious one.
Maybe I can add, I agree with Heinz about the cooling. The design is designed for taking away this power. So in principle, we should be able to go to somehow lower than minus 15. Nevertheless, I think you have to consider that now we are trying to balance because you have to protect for electrical isolation to parallel, and also you have to consider that what could happen if modules are touched with. So what we did in the past, we put glue that is the kind of glue that we have used now for the qualification of this module. That is between a glue and grease, and this can be or a little bit not uniform, or if you change the thickness for the nominal. In the past we put 70 microns, so it was quite well controlled. So all these things have to be considered. So, but from the average value, you have to consider design for the worst case. So I think so. I still believe that we are in the envelope, but probably the margin is not between minus 25 and minus 15 that are the range, but probably is something that is narrow.
The silicon heaters for these tests were there were 3 staves built like that. Silicon heaters were glued onto in exactly the same way we plan to glue on modules, which means corner with glues and the rest with the thermal grease. There was there were different staves built, one with face plates and some with a thick purlin coating. The thick purlin coating is bad, we're not going for that. The rest was really as we know now.
So what were the differences between the various measurements?
The measurements, the difference was, in one case there was no face plate on top of the stave, but a thick 70 micron purlin coating. And in the second prototype was the face plate 150 microns instead of a purlin coating.
You need to add paralleling coating. You cannot leave
5
because
microns.
the face plate is conductive with carbon.
No, 5
so you need
microns.
to add something that is lower. So we are considering something like 5-7 micron. That I think so. I think one of the issues is that how to deal with the paralleling coating that is not too thick because of thermal, and the other that is safe because of scratch or other things that is isolating.
Did somebody do an analysis of all the possible risks we are taking with 1000 volt in the center of Athens?
We went through where we can get hit with the bias voltage in general, because to be fair, I mean, we don't respect spark distances also for 200 volts in our designs. Okay, we have the gap of silicon to silicon, which is 200 microns. You may add the gartering distance, which gives a slightly larger distance, but still, I mean, count on the 200. There we plan to put a peak shim in between to avoid that one. We will include a 5 microns purlin coating on the staves to avoid sparks between the sensor and the stave surface. And the third thing, and this we haven't solved yet, is between the modules face the beam pipe. The beam pipe has a conductive layer on top. The nominal distance, the closest approach is the larger bypass capacitor, which faces the beam pipe. So those we need to pot or isolate by other means. This sits at a distance of the beam pipe of envelope-wise 2.5 millimeter. And the fourth area is the bond wire, the bias bond wire on the module flex that connects the module flex to the backplane of the chip. Okay? So for the bias capacitor and the bond wires, we need to try out how we can isolate them.
Remind me, in air, the IPC recommendation would be 10 millimeters for 1000
I don't know.
volts.
I just know that we don't respect it for 200
Or
volts.
5. I remember 500 volts was 2.5 millimeters. So 1000 volts probably is not less than, but that's IPC, that's for a dirty environment more or less.
I think we basically for the high voltage, we are trying to design such that we avoid. So we follow kind of maybe very stringent design rule, and we try to check this thing. One of the things is that we can do some partial test. For instance, let's say the flex or the cable, you can test before assembling and gluing to. But as soon as we start to put the module together, I think you cannot apply the final, in the system you cannot apply, in some cases we cover, but no, we cannot cover probably everything and qualify everything from wire bonding to component. You cannot, I'm not think we have a way of covering everything that is exposed to high voltage. So.
Yeah, this is not quite sure. I mean, we try to actually, because we can't go for IPC rolls, we have to cover it. This is what we look at. And the cover has the purlin coating, the big shim, module to stave and intermodule. And then one thing that we, the capacitor, we have to find the right high voltage isolation lag that we can glue on it, which holds the radiation. And the potting of the wire, the various potting, some that stay elastic, some that don't. Bottom line is, the first
because I got lost there.
I was just wondering whether you could, at least on the assembly, whether you could, if you just float one of the staves, so you basically connect all the voltages on the stave together, but then raise it to 1000 volts and just check that there is no breakdown with respect to the neighbours. Is there any way of doing the test other than, to avoid putting 1000 volts across the sensor? Then you might be able to do it.
Or you want to put, for instance, because I think we have separate few modules on the same stave, you can float this together. Probably, I think there are separate ground. I think.
Okay.
The cooling pipe, the stave
The cooling pipe is the cooling pipe. Yeah. Okay.
The
Okay.
end of the cooling pipe will be grounded.
Yes. Okay.
Staves are grounded.
I don't mean finally, but at a certain moment, maybe I think it would be worth to think whether we can float some module, not only one complete stave to the other, but when you assemble the stave to float one with respect to the other. I don't know.
Right. And the other
But to
question.
do a test is probably okay. You
Sorry?
can invent a way to solve the problem of the pipe for the test.
For an isolated test, but not for the whole detector
No.
set that we
Yeah.
count.
No. And my other question, because I didn't really get a strong sense of it from.
How did you deal with that? Yeah, that's what I wanted to say.
Okay, I think one thing that is different is you have a much more, because for instance, the module is not one next to the other.
But it's one over
Yeah, but you have this 250 micron, and then on top you have flex. So I think, and then in some cases the high voltage is a little bit, with the gathering is not really facing the stave. So
But you have not used any
no, I don't.
coatings?
No. In addition, there was not protection. It was not protection with Parilan on the stave itself.
But I believe that this issue that the field brings up, that is important, is an issue that you, in my opinion, you will not need to test all of your stave in the final assembly by running 1 at 1,000. It's also impossible. It is a sort of a thing that you have a project to reach this 1,000 volt qualification. What we've been told today is that in one case 1,000 volt is needed to, or close, is about the same between the two technology given the target irradiation, and I'm not surprised anymore because with 200 volts and 70 micron to deplete, it is very similar to 800 volts and 200 micron to deplete. But do we think this is driving our choice, this 1,000 volt? Or better say, do you guys see this, that you are developing stave, do you see it as a big challenge to meet the requirement?
We put it in what we haven't seen yet is, okay, our max operation voltage we defined as 1,000 volts. This means we select all the components, make the flex layouts with distances and all this sort of thing up to a test voltage of 1,500, okay? So we design for 1,500. As you know, some components like bypass capacitors you don't get for 1,500, so you usually go for 2 kilovolt components. Which means we respect our max operation voltage of 1,000 and max test voltage of 1,500 all the way through the design. No, I don't close my eyes. I mean, 1,000 is higher than 200, okay? At the moment, we haven't found a showstopper for 1,000. Okay?
My step in this discussion is very interesting, but I think it's very dangerous now to sit in this discussion and discriminate between technology. This, I think, is a detail of one of the applications, which maybe you can solve. We can find a reason that you are not able to solve. I think the real issue that we have to discuss here is different. Do we see something wrong in the other technology, or something wrong in the new technology they are bringing in? Let me start asking you this following question. For me, as I am simple-minded experimentalist, what I see is the silicon technology is the same when you start building this object 3D, and it's more or less apart the high voltage the same when you operate it. So there are no very big differences. The difference is that in one you drill a vertical hole inside the silicon, and you have a processing, certain number of processing in all this. But the question is, do you see drilling this hole in the silicon something which discriminates to this technology and make it more dangerous, more less reliable, or is too new? So, what is wrong? What you see wrong in this technology? Saying it right now, to give a reason not to adopt it in the next step of Atlas. Is that technology too new? Has not been worked out enough in details? Are we not sure about the aging properties? Tell me.
I guess a comment I have is that I would be interested in how the 3D process, or the 3D collaboration would respond if one of the vendors dropped out, because I think that one of the vendors has some unresolved issues and also has been tested less in fully bumped form than the other. So I think we need to understand the impact of not having that vendor available. And that is a response, I think, to your more fundamental question, because it is, I think, the 3D process, which is not obviously working in at least one of the graphs or one of the devices that we saw.
Can you be more specific in pointing out where you see it so evident?
Oh, well, it was we saw a graph from a device produced by FBK that showed inefficiencies in an unexpected region. So I think that's not necessarily attributable to the silicon, it's something about the technology. And it's something that is not appearing in the other vendors' devices.
This was, I think, this slide 31. And
Okay.
famous slide 31, but we will see others in another slide where it was fully compliant.
Well, but in addition, that vendor has had fewer qualifications, fewer devices that have been fully qualified. So we just have less information to be confident about.
So you think that for the CNM, they are only tested with the guard ring, and it may be not sufficient?
I'm just saying that CNM is more fully qualified than FBK. So I just express my concern as what if one vendor has to drop out or just can't meet the time scale.
Sally,
Maybe, okay, let's then move to this 3D discussion so that
I wanted to comment on Marzio's questions or comment that is once the sensors are fabricated, they will go through the same process into bare modules and later on around the beam pipe of atoms. What we have seen today, and is one of the clear signals that distinguish the two technologies, is that from the sensor standalone, the yield is quite different between the two technologies. Now, when you talk about yield of sensors, especially a pixel sensors, your capability to understand what is actually wrong is quite limited because you cannot probe channel by channel. So your explanation, several, are hypothetical. Now, it's the ground on which you have to base, on which you have to build your detector. Having a lower yield to start with, I am afraid cannot end up in a better yield at the end. It has the potential to go worse because you don't understand what is going on. You ask for long-term behavior. I cannot answer that question. I can only elaborate on the data that has been presented to us today. And this is a matter of risk assessment because the further step of bump bonding have been done with both technology. But as soon as you move from bare sensor to bump bonding, your statistics go down on the data we have seen today by a large fraction. It is a risk assessment, but you start with a lower yield from the beginning. That is something that to me has some value in one direction instead of the other. I cannot comment more on the question you asked, but that was a clear signal today.
I think, okay, the yield is more complicated device, yes. So it's more step respect to planar. So I think yield somehow is connected with a number of steps of it because you have to do this wafer. So I think it would be difficult even in the future to expect a yield that will increase much more than what we have. So this was one of the reasons that the 3D decided to stay with a single chip module instead of going to a larger surface like a planar, because it was considered that if you don't want to kill completely the yield. Then I think yield probably in some cases also in the planner you see that you have different curve. But I would say that the planner are more compliant for single defect, or there are probably different defect structure, and something are not really so important for the breakdown, for instance, of the planner. And 3D probably has some more effect on this that are connected maybe to some damage in the bulk, sometimes in the surface. Also, you have to consider that what are separated. They have a column that are separated, so you have P-spray, but there are very nearby structure. For instance, FBK, they have seen that for a breakdown, they did also planar structure, and the breakdown, you have seen that for the 3D is a little bit more than between 40 and 50 volts, and planar is something like around 60. So there is the intrinsic breakdown. So they are basically not that fast. So I think this is be considered. Considering the expect, I haven't think much on the FBK behavior with the column inefficiency. I think there are, we have to look a little bit at these columns. So in the case of FBK, there are completely true column, okay? In the case of CNM, you have about 15 micron that is not going completely through. So I don't know how you weight the field potential lines, whether you collect, in the case of the 3D, basically you have this column, and where you don't see efficiency between the 2P column, I think is because you have really weak field. Basically, it's not collecting the charge. So either you will move more higher voltage, but you are limited by the breakdown. Okay, so you have to sit there. So the other thing that you can do, to my point of view, is just reduce the threshold. So trying to go to 3,200 because they saw that the average charge is high, but not there. So I don't know whether this effect is due because you have a completely column through, so basically you don't collect charge that could be underneath. And that,
I mean, it's at 15 degrees.
yeah, but at 15 degrees, just eating this, it's not 50 degrees, you don't collect.
It was wide.
Sorry?
It was wide, the region. It was not just the width of a column, it was much wider.
Okay, you have to consider that we don't have a result in the track's resolution, so it's wider because depends what is the resolution, and we put quite some material, so multiple scattering. So I would like to see what is the reconstruction of the track. So you have a dip. If you look at the picture, it's 250 microns, so it was something like 50, 60 micron. But I think this is mirrored by...
15 micron wouldn't save you. I don't think it's an issue of the 15 microns that CNM doesn't go through.
Marco, one thing in the, I mean, there were two
I don't know, it's just something that I say for thinking. Maybe there are some other issue, but I think you have, the way to compare is really looking at what is the possible.
And this is the very reason why we plan on 10 batches instead of 6 batches. The sensor, the batch numbers, the size is the same, 22, 24, 25. But just to make the difference between the yields, we produce more.
I probably was not clear. I was trying to correlate with the question of Mark. That is, what do you guys know about this new technology and how it will behave in 6 or 8 years of operation? That is roughly what you are aiming for. And the answer, honest, is I know nothing about it, as probably most of us don't.
You know what?
You start with a lower yield, you are likely to have more problems in the future. That was my extrapolation.
Heinz.
Very simple and probably very wrong.
But just to rephrase what I thought he was thinking is we don't know anything about the inefficiency, the part which are not and the reason for it. And maybe there are some of these reasons which will affect us later on in the operation of this object.
Okay.
I have another worry. I mean, this, within the same production batch, the wafer-to-wafer fluctuations because there seem to be coherent effects underway. So this could point that one of the processing steps, you know, is just at the edge. And I mean, if you, because they're supposed to be identical. I mean, they run in the same sequence. Yet you have one wafer which is just beautiful, 100%, and you have the other wafer that is just marginal. So, I mean, if it were just random defects, then I would say, okay, we see something like 50+%. And I could be semi-confident that by the end of the year, there might be lots of them that were giving, I mean, that were out of specs. So they were much larger than a normal Poissonian distribution, where you would say, okay, I have 50% on the average, and they're somehow distributed. There were wafers that were really bad, and there were wafers that were really good. And out of that, there comes a mix of 50%.
Okay, but we only have the 9 wafer, and the Poisson distribution. I think they can analyze if it's really the Poisson-like one.
Also the way all the 3D wafers that you've looked at, now is 3 wafers of it, plus the one with the...
I thought I looked at 9 wafers.
From the,
From
okay, from the
Atlas 10,
different...
yes.
Yeah. This is,
I'm referring to their pre-production results.
so, no, okay, I meant the one assembled to modules. Okay, okay, so, okay, then yes, I mean, from the reproduction one, yes.
Anyway, I think I doubt whether we know all the details actually concerning the technology. I mean, between these various batches, what they did to the technology, whether it's really a stable technology or it's still a technology under development. And we know, I mean, if you do very little changes to the technology, you may end up with a catastrophe. Okay? I mean, it wouldn't be catastrophe if we had 3 years in front of us. I mean, having this tight schedule, any single wrong part, I mean, it would be a big impact on our schedule. So, I mean, I must say, the answer I got about my question concerning the stability of the technology was not was only from one vendor. We have to say there was no comment from the other vendor.
If I can add to what you're saying, you just pointed out that actually the columns are a little bit different between the 2 vendors. What was a lot more clear in the last time we met is that one vendor is using P-spray, the other one is using P-stop. The 2 vendors deliver a product that is different one from the other. I think we have all indication that both products meet specification. But I'm again back to the question of Marzio. That is a little bit the bet we are placing on using a new technology, not any longer on a test beam, but on a real detector, and probably on the layer that you need the information the most. You might be placing 2 bets if you go with 3D, because it's not only 2 different countries that are producing them, but the way they are producing them has many differences once you go and check the step-by-step process. It's just something that didn't come out so clearly on the presentation today, but I think it was clear the last time we met.
I agree with you. I think this was made clear, but the idea is to have the same floor plan, the same thickness, the same layout, but the process is different, and basically was both trying to get the performance that you need. I think they met, and I think it is in the limited time. I think this has been demonstrated. clearly there are some, if you consider that most of the development of this technology is since last 6 months, I think there was a very huge progress. I think, and I think to me, I think many things are demonstrated. But I think, to me, as even more, there are also things that to me are not very well demonstrated on the planet to run at 1000 volt in a stable or in a system and all this kind of thing. So I think it's a matter of balancing the two things. I agree that the planner, in principle, with a low enough threshold, they collect enough charge, but okay, was already seen in the test beam that operation was somehow more, from the point of view of the operation, was more difficult. So now for IBL is clearly we do something that is better by design, but this doesn't mean that I think still from the point of view operation, the 3D are simpler than planar in many corners, and I think one of the corners that has been less tested is high voltage.
Nani, can you remind me of the statement? I mean, I haven't heard that from Philip, that the operation of the planar in the test beam would be more difficult than the operation of the 3D?
There was the comment about the difficulty to set the bias. You remember?
But
Because of the temperature.
this was a cooling issue?
It was cooling issue, yes.
Okay, so that was because the sensor could not be brought to -15?
Basically, with the system, the cooling system.
Back to that, maybe I understood it wrong. But what he said, what he presented as difficulties to operate that detector at 1000 volt was associated with given the same dose, even if they are at 2 different voltages, they are the same current. That problem happened on a planar sensor, but unless I am mistaken in my logic, it could have happened to, maybe there is a flaw in my logic. But.
Could I?
The only thing is in case, I mean,
Something wrong in the way this technology has been built up, or the fact that we are going into this technology. The question is really, do you see something wrong in this technology?
I mean, could I perhaps ask the question a slightly different way, which is, where we have failures, do we understand them? And, you know, this to me, ignoring the question of performance at the end of the lifetime, it does seem to me that, you know, people are concerned about the fact that the yields are different for the two. Do we know where the breakdown, I mean, you made a comment that FPK had P-type planar prototypes we had made with CNM was too high, and I just wonder whether it's those optimizations which are still, you know, still needed.
I think a cross-check, but I think the requirement for the 3D, because you have to separate words for the 3D. So I think it's to be considered in this way. So
I mean, I'm just, you know, when the yields over 90%.